Having a detailed discussion about a series RLC circuit, let us now have a quick look on a parallel RLC circuit, where the left-hand side of the circuit is a Norton equivalent consisting of a current source as well as a resistor Rn. Uh, the circuit on the right hand side, the non-shaded part, consists of two parallel components, are an inductor and a capacitor. The current through a capacitor is assumed as IC. The current in an inductor is assumed as IL. So the current going in the unshaded part is combinedly called I of t. Whereas we consider the current in a resistor as IR and the current of the source is IN. Similarly, we consider the voltage across an inductor, capacitor, and a resistor is called V of t. Hence, by applying the Kirchhoff current law, which states that current entering in a node is equal to current leaving, uh, so applying Kirchhoff current law here, In of t is equal to IR of t plus I of t. Similarly, applying Kirchhoff current law here, it is I of t equal to IL plus IC. Now combining these two equations, we generate a general equation of a parallel RLC circuit, which is IC plus IR plus IL equal to IN. Once a general equation is obtained as IC plus IR plus IL equal to IN, we can replace the value of IR according to Ohm's law as V over R, because we know the voltage across inductor, voltage across capacitor, and voltage across resistor are same, equal to V of T. So IR may be replaced by V over Rn. Now, if we want to write this equation in terms of IL and form a second order differential equation in terms of IL, then we have to replace V of t and IC of t with by IL. By use of the general uh, equations corresponding to inductor and capacitor, VL is equal to LdI over dt. This can be straight away put inside as V of t, because VL and V of t are same in parallel circuit. So we have an expression like this: IL plus IC plus V is replaced with LdI over dt and Rn is as it is. So we have an expression like this in an equation. In this expression, we can see that everything except IC is in the form of IL. If we want to convert write IC in terms of IL, we use this expression of current in a capacitor. IC is equal to C dVc over dt. Here the value of Vc is replaced with V of t or VL of t, which are same in parallel circuits. So VL of t is LdI over dt. If we put it here, we get C d over dt into L or LdI over dt. So it will become LC d square over dt square IL. So putting this expression of IC into this equation, we get an equation as in the form of LC d square IL dt square plus L over R and DIL over dt plus IL equal to IN of t. This is a second order differential equation. Comparison of equations obtained in series RLC circuit and the equation obtained in parallel RLC circuit leads us to show the principle of duality in between series and parallel RLC circuit. It can be observed from these equations that the variable Vc of t and IL of t are dual of each other, where Vc is whatever Vc in series RLC circuit is, we can replace it with IL in parallel RLC circuit. Similarly, L and C are dual of each other, RT and 1 over Rn are dual of each other, and voltage Thevenin and Norton current are dual of each other, as is represented in these equations. In order to obtain a zero input response, we set in equal to 0. Therefore, we get a second order differential equation of this form. In order to solve such an equation, we again let IL equal to k e raised to the power st and obtain a characteristic equation of this form as is previously done in solving a second order differential equation of series RLC circuit. In this way, we obtain two different roots which may be complex conjugate, which may be real and distinct, or which may be repeated. So these the solution of differential equation will be done accordingly in three cases as described in the next slide. So here is the summary for parallel RLC circuit, that is when the discriminant L over Rn square minus 4LC is greater than 0, we will get the real and distinct roots in the form of minus alpha 1 and minus alpha 2. In this case, the response of the system will be overdamped and the equation of current in the conductor will be K1 e raised to the power first root times T plus K2 e raised to the power second root times T. Similarly, if the roots of the characteristic equation are repeated, then which is possible when L over Rn square minus 4LC becomes equal to 0, then the current in the inductor will be K1 e raised to the power minus alpha t plus K2 times T times e raised to the power minus alpha t. Don't forget this t in case of repeated roots. Similarly, when the roots of the equation are complex conjugate of the form minus alpha plus minus j beta, then alpha minus alpha is the real part and beta is the complex part of the equation, and the response of the system, which is the underdamped system in this case, the response will be k1 e raised to the power real times t cosine of imaginary times t plus k2 e raised to the power real part times t sine of imaginary part times t.